So we're at an exciting time. We're finding out that there's a whole new side of calculus that's going to solve some really important questions for us. But I did leave you in the last talk with a dilemma. So why don't we just kind of talk what we're looking to try to find and what the dilemma is and see if we can solve the dilemma. So we've got a function y equals f of x that's defined from a to b, and I've tried to convince you, and you're still taking my word for it, that something called the signed area between the function and the x-axis is going to be really important. And signed area isn't that complicated. It's just area as you've always assumed it. It's the area, the space on a two-dimensional surface in between the lines. So it'd be just area like we normally think of, except if the function happens to be below the x-axis, we're going to consider that part of the area as negative. So that contribution to the total signed area would be negative. This contribution would be positive. So in this particular case, overall, you would have a positive signed area. Anyway, if that's really important, then how do you get it? Well, we kind of, from geometry, have learned some formulas how to find area. But that really much involves straight lines. So if we had if all this function was made up of straight lines, we would have triangles and rectangles, which we could find the area, which means we could find the signed area. Or if it happened, the curved area happened to be a semicircle, we could do that. The trouble is, we're looking at a very small percentage of the total functions that fit that category. So we have to come up with a new way of getting signed area. So we came up with an idea, since we know how to take the areas of rectangles, maybe divide from A to B up into n sections. And just take a section right here, say from xk minus 1 to xk, two values, and pick some value in between that, which could be at any place in there, and call it c sub k. And then we just took this height, which we called f of c sub k, the function value, times the width. If you take x sub k and subtract x sub k minus 1, we call that width delta x sub k. And basically what we have is the area of this rectangle. And if it happens to be below the x-axis, like that, this function value would be negative, so you would be finding signed area. So it's doing exactly what we want. Of course, we have n of these rectangles, so we have to add them up from k equals 1 to n. So we have a way of doing it, and so we gave this thing a name. We called it a Riemann Sum, after mathematician from the 1800s, George Bernhard Riemann. The trouble with this, it's a really good idea, except it's only got n rectangles, and you get a little bit of error up here because the rectangles don't completely mesh with the curve. So we came up with another idea. Let's make the rectangles really, really skinny, infinitely skinny, so that they really become straight lines. And then we don't get any of this error. Well, the way we do that is to take the limit as n approaches infinity. Or we could say as the largest partition size approaches 0. I kind of like this way as just saying we're getting an infinite number of these really skinny rectangles, and then we can get the exact signed area. So we had a method, and it's wonderful. In fact, we even gave this whole thing another symbol. Instead of making this summation sign and making it a special summation because you have an infinite number, we could just make a big S that Leibniz, the German mathematician, thought of as a summation, but a supersummation. And then in place of f of c sub k, we could just write f of x, and in place of delta x of k, dx. And we even called this the definite integral. But it really didn't do anything. This is what really does it. And it's a great method. And we tried it on the function f of x equals x squared, a parabola from 0 to 5. And we found out that it worked. In other words, in place of f of c sub k, we put x sub k squared. And in place of delta x sub k, this width, we took this total distance of 5 and divided it up into n rectangles. So each one was 5 over n. And then we took the summation. And then at the end, we took the limit. And I'm not going to go through this whole thing again. But when we did it, we found out that you can't do any algebra with x sub k. So we came up with an expression for x sub k. We said, here's 0. This first number is 5 over n, then 10 over n. By the time you get to here, you get k times 5 over n. And we put that in place of the x sub k. And then we could do some algebra. Now, the only thing bad about that, you still end up having to add up an infinite number of things. And that, in math, is a hard thing to do, to add up an infinite number of items. It just so happens, as you can see, this k squared right here, it came down to adding up an infinite, as n approaches infinity, an infinite number of these k squareds. We had to add up 1 squared plus 2 squared up to n squared. But we said there was a formula in algebra that did this. It got it all in terms of n, and then we were really able to take the limit as n approaches infinity. So we were able to do it. And if we did a little bit more practice, we found out if instead of just having x squared, you had an x in it, we had this other formula that kind of Gauss showed us how to do. And if we had an x cubed in our polynomial, then we had to use this formula. So all well and good if we're dealing with polynomials of degree 3 or less. The trouble is, there's so many more complicated polynomials and so many other kinds of functions. And as it turns out, there's no special formulas like this that allows us to do this calculation. That's the dilemma. We've got a good way to find an infinite Riemann sum, to give an exact value of our signed area that we're looking for, that's going to be so valuable. So, sorry to kind of repeat everything, but we really summed up what we're looking for, and we really summed up what our dilemma is. So let's try to solve that dilemma. How do we solve this infinite Riemann sum in a more simple way? Something that we can actually do and don't get flustered when we get to a point where we can't go any further with the algebra. So, I'm coming down to this picture. I got this function y equals f of x, and let's just say it's a continuous function. So I've got y equals f of this continuous function, and we're going to assume that y equals f of x has a bunch of antiderivative functions. And let's just assume that I'm graphing here the antiderivative of this function y equals f of x from a to b. And I'm dividing a to b up into n subintervals. From x0 to x1, xn minus 1 to xn is the last one. And we're even going to take this kth subinterval right here, and I'm going to blow it up to bigger size here, just so we can analyze this one interval. Now, you might not know why I'm going to do this right now, but let's figure out what you would get if you take this function big F of x, the antiderivative of this function, and plug in b and plug in a. Now, what would you get if you did that calculation? Well, f of b is really f of x sub n, and f of a is f of x sub 0. So I can write that this is really f of x sub n minus f of x sub 0. But sometimes when I go to write, I have all this extra space in here that I have to fill up. So what I'm going to do is fill it up with a bunch of zeros. I'm going to add minus f of x sub n minus 1 plus f of x sub n minus 1. Then I'm going to go, because that's just 0. Then I'm going to go minus f of x sub n minus 2 plus f of x sub n minus 2. And you can see that I'm filling up the space, and it's really the same value because I'm just adding 0. And I'm going to keep doing this. And the way you do that is just to put a few dots, and then I'm going to go minus f of x sub 2 plus f of x sub 2, and then minus f of x sub 1 plus f of x sub 1. So I've filled up all that space, and it's still a true statement. But it looks kind of complicated. So what I'm going to do is pair these up. I'm going to take these two and pair them up. I'm going to take these two and pair them up. And I'm going to keep doing that all the way down the line until that's my last one. So I have all these pairs, and I notice that all the pairs look the same. F of x sub 2 minus f of x sub 1, f of x sub 1 minus f of x sub 0, they all look like f of x sub k minus f of x sub k minus 1. This k is always one bigger than the k minus 1. 2, 1, 1, 0, and n minus 1. And I can write this summation of n pairs by doing the summation from k equals 1 to n. Now, this is where I don't really like this expression. I don't really like what that looks like in here. So I'm coming back to my picture over here and said, if I take these 2 points on the graph and I draw in this slope right here, what is the slope? It's the rise over the run. And the rise is this f value minus this f value. It's f of x sub k minus f of x sub k minus 1. And the run from here to here is x sub k minus x sub k minus 1, which we've been calling delta x sub k. So that's the run. And then I remembered back and said the mean value theorem guaranteed that somewhere between here and here there was a value where the slope was the same as this average slope. The instantaneous slope right here is the same as this average slope. So let's call this point c sub k. So that means that the slope of there is equal to this slope. And what would that slope be? It would be f prime of c sub k. So I can now use this to come up for another expression for this numerator. I can just say this numerator is this times this. Now, if this is going to be important, we better be careful. We use the mean value theorem. Can you always use the mean value theorem? No, this function has to be differentiable. That means in this area, the derivative has to exist for every value. Well, is it true? Well, if this is the antiderivative of little f of x, by the definition of antiderivatives, we know that the derivative of big F is little f. And we know that f of x is continuous. So every value of x has a y value. That means that big F of x, the derivative, has a value at every value of x. So it is differentiable, and I can use the mean value theorem, and I'm still doing fine over here. Now, but what's another way of writing big F prime? We just said we can write it as little f. The derivative of the antiderivative is the function. And by the way, where did we start? All of this was really equal to that. So we can say this is equal to f of b minus f of a, which is a constant, because you're just putting two values into a function and subtracting them. So if this is a constant, if I take the limit of that, it's going to be the same thing. So I'm going to take the limit of both sides. If this equals this, then the limit of this is going to equal the limit of this. So I'm going to take the limit as n approaches infinity. And what do I have? I've just proved that this infinite Riemann sum that I'm looking for a value for, a way of finding out what it is, I found out a way. I can just take the antiderivative of this function, plug in the two endpoints, and subtract them. Wow, this is amazing. This is so amazing that we're going to call it the Fundamental Theorem of Calculus. FTC. You don't call things fundamental unless they're pretty important. What this does is it links differential calculus, what we've been doing, to integral calculus, what we're going to be doing the rest of this year. So it was a pretty amazing accomplishment. Now, usually you don't see it written like this. Usually you see it written, the integral from a to b of f of x dx. It just looks nicer that way. And most of the time, we're going to be dealing with this symbol rather than this. So this is just another way to write it. Remember, this is just a fancy way of writing this. This is going to be our goal for a long time, is to be finding these exact signed areas. So I'm going to even put 2 stars on this. This is going to be so important. So let's shift from here over to the other board. On the other board, we'll do a few examples where we use this fundamental theorem of calculus. Find some signed areas. Find what this definite integral is. So here's our first example. We're going to find this definite integral, which, just to get it in your mind, what are we finding when we do this? We're finding the signed area between this polynomial and the x-axis between -1 and 2. Now, I'll be honest, we could really do this with an infinite Riemann sum because this is a simple polynomial, but it would take quite a few steps and quite a bit of algebra. So let's use this new fundamental theorem. What does it say we do? We take the antiderivative of this function, which we now know how to do. It's 2x squared minus 6x cubed over 3. So there is big F from our formula. And we're going to plug in -1 and 2 and subtract them. And this is just the way we usually write it. We put the antiderivative here and we put the lower and the upper limits of our integral here. And that means that we're going to take this, plug 2 in it, and then plug 1 in it, and then subtract it, and that's going to be our answer. So if I plug 2 into this, I get 8 minus 16, and if I plug -1, I get 2 plus 2. So altogether I get -8 minus 4, or -12. That's the signed area. There must have been more below the x-axis than above the x-axis, and that's okay. That negative is going to mean something when we actually get into word problems. Okay, let's try one that's a little bit harder that we couldn't do with algebra. So, without the fundamental theorem, there'd be no way of solving this problem. But now let's see if we can do it. The first thing we do is take the antiderivative. So we go x to the, it goes up by 1 to 4/3 divided by 4/3, or times 3/4. And then I go plus, and this goes x, goes up to 1, x to the 2/3 divided by 2/3, or times 3/2. And I go from 1 to 8. So first I put 8 in here. Well, the cube root of 8 is 2. 2 to the 4th power is 16. Divided by 4 is 4. So I think if I did that right, you get 12. Do the same thing with 8 to the 2/3 is 4. So this becomes 6. And 1 to any power is just 1. So you get 3/4 plus 3/2. So altogether you get 18, and you're subtracting how many fourths? 3 plus 6, you're subtracting 5/2. Or let's see, let me make sure of that. This is 6/4, 9/4, so it's 2 1/4. So altogether, you would end up with 15 3/4. If I made a little mistake, sorry. But I'm pretty sure that's the answer. In any case, we have a method to solve something that's a very complicated function that we couldn't have done any other way. Well, now let's go from just finding a definite integral to use a definite integral to find an answer to a word problem. Find the area between the curve y = x² - 1 and the x-axis from 0 to 2. So always a little graph is helpful. So if I put in 0, I get -1. If I plug in 1, I get 0. And if I plug in 2, I get 3. So I'm on a portion of that parabola. And I'm trying to find the signed area. No, I'm not. I'm trying to find the area between this curve and the x-axis. So what I want to do is find that area. But I've got to do it by using definite integrals, which find signed area. So the way I'm going to do this is to go from 0 to 1, f of x dx, but knowing that the signed area is going to be negative and we want positive area, we put a minus sign in front of it. And then we go plus, now because this is above the x-axis, the integral from 1 to 2. And now we just use that fundamental theorem of calculus because it's going to be 2 signed areas that we have to find. I can get all set up like that. What's the antiderivative of this? It's x cubed over 3 minus x. And it's going to be the same thing over here. If we kind of get used to the fundamental theorem, we're always going to be doing this same thing. So if I plug in 1, I get, do it in a different color, I get 1/3 minus 1. 0 is going to give me 0, 2 is going to give me 8/3 minus 2, and 1 gives me 1/3 minus 1. So altogether I get minus a negative 2/3, which means this area is 2/3. Then I go plus, and this is 8/3 minus 6/3 is 2/3, minus a negative 2/3 is plus 2/3. So this area in here must be 4/3. So altogether the total area is 2. We found what we were looking for. We found a use of signed area to find area. And let's try one more of those. And then we're going to really have to wait till the next chapter to get lots and lots of uses of signed area. So now we're going to go to a trigonometric function. Y equals 3 sine of x. Well, we know it goes from 0 up to 3. Then it goes back down to 0 again, and then it would go down to -3. So what we're trying to do is find all of this area in here. So we could go the integral from 0 to pi of 3 sine of x dx, and that's positive, so the integral is going to give us exactly what we want, but this then we'd have to go minus the integral from pi to 3 pi over 2 of the same thing. So, taking antiderivatives. What's the antiderivative of 3 sine of x? It would be minus 3 cosine of x. And the same thing here. So, plugging in the numbers. The cosine of pi is -1, so this is 3. The cosine of 0 is 1, so we get -3. On this side, we get the cosine of 3 pi over 2 is 0, and the cosine of pi is -1, so we get 3. So altogether we get 6 plus 3 or 9. That would be 9 square units of area in there. Now, some of you are probably thinking, because we have knowledge of the sign, we could have even made our life easier by just saying the total area is going to be 3 times from 0 to pi over 2. So we could have gone from 0 to pi over 2 and forgotten that completely, but then just put a 3 out front. And I think you can kind of see you're going to get the same answer, because the sine of pi over 2 is 1, and the sine of 0 is 0, and 3 times 3 is 9. So, 2 definite integrals, 2 uses of definite integrals to find area between the curve and the x-axis. Now, because we're going to use these definite integrals a lot, what are some properties we can use? Well, you got to go back to what a definite integral is. It's just adding up a bunch of things. So if everything that you're adding up had a constant in front of it, could you factor out that constant? Yes, that's an algebra idea. So we could say that this, we could just take the constant out front and do that. So that's one property. I could have taken this 3 right here, right out in front, and not left it in here if I wanted to. Now, what's the integral from a to a? What's the integral from 2 to 2 of x squared dx? Well, there's 2 ways you can look at it. One, there's nothing between a and a, so there's going to be no signed area. The other way you could do it is use the Fundamental Theorem of Calculus and say the antiderivative of that is big F of m, and you plug in a and subtract them, and you get big F of a minus big F of a, you get 0. So if you ever get a definite integral that goes from a number to a number and it's the same number, the answer is always going to be 0. And notice I used a different letter here. Remember, these are dummy variables in a definite integral. It wouldn't have made any difference if I had made this x or t or some other letter. Now again, because definite integrals are just adding things up, we know the order of adding doesn't really matter. So we could add up all the f of x's and then all the g of x's. And do them separately. That seems to make, this is a theorem, but it's a theorem that, just makes a lot of sense because of our properties of addition. And it also works with subtraction. It doesn't work for multiplication or division. Now, 2 more. What's the integral from a to c, where, say, c is at one end and b is somewhere in the middle, and you're trying to find the integral from a to c? Well, again, it doesn't really matter if you're looking for signed area, if you do the whole thing or if you take this one and then this one. So you could take the integral from a to b, f of x dx, and then add the integral from b to c. I'm hoping all of these are just pretty much common sense from our knowledge of arithmetic. And the last one, the integral from a to b, is that, I wonder, the same thing as the integral from b to a? I don't think it is, but I bet you there's a connection. What would this be? With the fundamental theorem, it would be the big antiderivative of b minus the big antiderivative of a. That's what the fundamental theorem says. And this one would be just the opposite. So since it's just the opposite, I can do this. I can say the integral from a to b is the opposite of the integral from b to a. So these are just some properties that we will use when we do definite integrals. The big takeout for today is that we've solved our dilemma. And it was a big dilemma, and we found out how to find the signed area between a function and the x-axis for any function that we can take the antiderivative of, and that's a whole lot of functions. So I hope you are as excited as I am about that. Have a good rest of your day.